Continue with the cheapest route algorithm. Like end of the previous video, I say, if we say this node is the start node, we just consider actually this node and this node both are the end node. But here you will see if we already visit the end node one time, we find out 10 plus 1. Before, when we do the shortest route, we can consider this one already is the best solution. That's because the age doesn't have weight. But now since the age have weight, then later maybe you see here, we will have another route, but they have the total cost is only 1 plus 1 become 2. So they will be cheaper than the previous one. So on the other hand, when we earlier we say any nodes, if they've been visited, we just skip. It's not work. And anytime when we find if this node is visited, right, I just need to compare what their old cost. If the new cost is smaller than the old cost, I need to update the cost. So that's why here you will see the cheapest route, the algorithm will become like this. So here the initialization the same as before. When we pass in the database, we need to mark all they are not visited. So then they have the proof equal to -1, the 0, cost equal to 0. So we're still using the queue. So then you have your start node pushed to the queue. So right, you still have the while loop, is to-do list, is the queue is not empty. But when we pop each node, we try to consider this node is under consideration. Then we want to visit all the nodes for their neighbor. Remember before we say neighbor has been visited, we just continue. But now we cannot do that. Actually, we need to cross that out. And also the neighbor cost is not only the 1 plus the cost for the new node consideration. Actually, they are changed become like this. We need to calculate the new cost. Of the new cost is equal to your node cost plus your considerate node cost. So you need to use in your considerate the database I cost plus now your neighbor age cost. So if this new cost is smaller than the original cost, then we need to update that. Otherwise, we just not do nothing. So that's why here your if statement is if the neighbor being visited and the new cost is not less than the current cost. So then this one I don't need to worry. But if they are cost is less than the current cost, that's why I need to set the neighbor's cost equal to the new cost. So we only consider if they can update the new cost, right? So that's we update. Otherwise, we just continue. But not only you need to update your neighbors the new cost, but since your route changed, right? So that's why your neighbor's proof, you also need to change, become the new node under the considerate. Yeah, we still can mark the neighbor is visited, but it's just not, we will skip that. So then you still push your neighbor index into the to-do. And also we see here, earlier when we find the neighbor is the end node, we just finish. Okay, but here they all need to cross out. So that's why I see the whole thing here. You will do your to-do list queue to finish the whole thing like that. So then afterward, of course, you will find, you need to go over all the possible routes to find the shortest route. So afterward, how you will build up your route using the stack, that's the same thing. So actually this one, I already give you also the find the cheapest route. You have your solution file for this one, how to do that. So that's the same thing. You can go to your the pages for the lecture. So underneath here, you will see you have the bfs_cheapest.cpp. So this one is implement the algorithm we have here. So you can refer to that. But one thing is the most important thing I want you to you go over this example by yourself, because the most important thing we want to do is I want you to introduce you another algorithm. We call they are Dijkstra algorithm. So this algorithm actually still kind of based on here, but we just want to ask you, do you have any other better solution? So instead here, the Q, we just continue to push in, right? So then we need to go over all the possible routes. So can we make that a little better? So this one, right, we can't. So we can do that. So this one actually is the Dijkstra algorithm. So this algorithm, what they do, so fundamentally they just do is you see from beginning. So when I have my star node, I go over all my neighbor for the first level neighbor, right? You see they maybe be 10, they maybe be 1, they maybe be 15, so they maybe be other number. So earlier we all push those nodes, the neighbor node, into our queue. So the queue actually do nothing. But one thing is, how about I can find a way. When I push those nodes into the queue, right, I also including those cost information. Then I don't push to the queue. I push to priority queue according to the distance here. So the distance here, the priority queue, we're using the smallest. Yeah, because we try to find the cheapest route. So this priority queue actually will have the cheapest one on the top. So then after you have the cheapest one, right? So every time when we want to go to the next considerate node, I will start from the cheapest link now. So since every time you go to the each level neighbor, you will have the cheapest link have the higher priority in the priority queue. So when we pop out one by one, so when you pop out, of course, we pop out this considerate node. I still need to go to this considerate node, all the neighbor, right? But one thing is, because we always try to update the total cost into a priority queue, so they always have the lowest total cost on the top. So that's why when you go over, if we find any node, they are met the end node. If you're using the priority queue, then this end node actually is the cheapest route. So that's what we will apply for the priority queue. So this one is in order, instead to using the queue for the to-do list, we were using the visit node index and the cost using a priority queue to have the lowest cost is always on the top. So if we can do that, so the first time when we find the end node, we finish. So the next one, the most important thing is how should we build the priority queue? So what is the priority queue data type? Because we need to have a node information. We also need to have a cost information. So that's why here, the next one in order to build up this priority queue, we add a new struct. So this node struct we call the terminus. So this terminus actually including the earlier we say the index. So that's consider index. And so far, this index, come to this index, the cost is. But also because we need to update the information, right? So that's why here, when you have your index, you also need to have your proof information here. Because one thing is we need to know the previous node, what there is, so that we know which route we are really looking for. So then after we have this terminus is the object for our priority queue. So don't forget, before our priority queue, or here this one we don't use R on priority queue, we're using the C++ STL library priority queue, but they still have the bigger value is the higher priority. So that's why after you have this terminus is the node, the data type for the priority queue. So you need to redefine your less than operator. So then you see we will do the opposite. Actually, if we have A and the B, so then actually we return the B.cost less than the A.cost. That means we reverse the logic. So now this one is your pseudocode for the Dijkstra algorithm for the cheapest route. So you see the initialization, they are still the same. So we still passing start node, end node, and our database. So to initialization is still the same. You have all the costs equal to 0, the proof equal to -1, and its visit should be false. So now the different thing is you need to have STL priority queue for the terminus object. So then you create a terminus object for the start node. For the start node of the proof equal to -1, cost equal to 0. So this one actually we push that into our priority queue to-do list. So then you see here, we still have the while loop. Okay, so the while loop is for the priority queue is not empty. So so we need to pop out for the considerate. So then you will see here, you pop out the top from the priority queue. So then you will using this one as a considerate node. So if this one already been visited, this time we can continue. Right, because one thing is, remember, you're always using the priority queue, right? So the first time you visit this node, you already know this node will be the lowest cost. So then if not, then we just mark the considerate object as a visited. So this one is update the info in the database. So you update the database is visited. So then you will set its cost of the terminus. You will update the proof to the terminus. So if the terminus actually is the end node, then congratulations, you just finished. But if this node is not the end node, then we need to continue, right? So for each of that nodes unvisited neighbor, so then you need to be careful. We need to update we need to create each node is a terminus object for that neighbor. So then we need to set that cost for that node plus the age cost. So then we set this proof is the considerate node index. So this one is like earlier we update the cheapest route. So then you will push the terminus object, go to the priority queue. So to do a priority queue, so that's why you see they will go back to the priority queue. So then they will rearrange their order. So after you're done, you see, then we will do until they are not empty. But one thing is possible when you find the end node is the term considerate node is end node, then they just finish. So after we're done, right, you just need to build up a stack of the all the entries. So this one will be the same. You will return back a stack. So be careful in the pseudocode here. Actually here, when you have your considerate node, you want to update the information. You need to update the database information from the terminus. So that's why I want to show you the while loop. So while the to-do priority queue is not empty, so we will have a considerate node. So if this one is visited, actually we can just skip because we already find the shortest route. But if not, you will see here, we need to update back from the terminus we pop out back to the database. So we will need to see this considerate node index is visited. So that cost is from our terminus cost to the database cost. And we have the proof one. And also when you visit the neighbor, you need to be careful for the syntax here. I don't have enough time for this video, so you need to check to see if you have any question.